It turns out that once we've learned the frequency patterns of different expansions, different rules, different lexical rules in a grammar, we can actually use that to figure out the structure of new sentences. That's called parsing. So a probabilistic context-free grammar, such as the one we just learned from data, can be used to select a parse for a sentence. So the issue here is that sometimes the words in a sentence can construct different structures. So let's look at time flies like an arrow, where it's supposed to be analyzed as time flies like an arrow, versus fruit flies like bananas, which is not supposed to be analyzed as fruit flies like bananas, but instead as fruit flies, the little bugs, like bananas. But it would be a reasonable syntactic structure to say fruit flies like bananas. It's just a much less likely analysis of this sentence because fruit flies do in fact like bananas. Okay, so the goal of parsing under a probabilistic context-free grammar is in order to choose the right structure for every sentence. So we parse by finding the tree with the highest total probability that yields the sentence, meaning the leaves of the tree are the words in the sentence. And total probability is just the product of the probability of all the different rules that are used along the way. So here's an algorithm for finding this best tree, which is just try every rule over every span of the sentence, but make sure that when you use a lexical rule, it actually matches the word at the bottom. So let's say we're trying to parse time flies like an arrow. Well, we just start trying rules. So we'd say things like, oh, maybe the whole thing is structured as a noun phrase followed by a verb phrase. I don't know whether that works out. Let's try. Let's try to put a noun phrase down. Here's a noun phrase. I know there's a rule that says I can write down a noun phrase as just a noun. And the lexicon has noun rewritten as time. And that's important because that means we've validated the structure that we've built so far using an element from our lexicon. Now, in order to build this whole S, we need a noun phrase followed by a verb phrase. So we need some way of rewriting the verb phrase, let's say as a verb, followed by a prepositional phrase. So we try that out and we see, oh yeah, flies can be a verb. The Z means a singular, like he flies. Okay, now we have to see whether it's possible to analyze this as a prepositional phrase. It turns out it is if I use that lexical element and that analysis of a noun phrase. Now this particular structure happened to work out. I planned it that way. But what your algorithm is going to do is actually try every expansion of every possible tag that we reach along the way over every span and just see which ones actually work out and which ones don't. So sometimes you won't be able to build a particular structure because the lexicon simply doesn't support the tag to word patterns that you need. Okay, so that's our algorithm. Let's take a look at its implementation. So here's a file called parse.py, the last piece of our puzzle, which takes in all of the lexicon and all of the grammar that we've learned so far. So this whole thing is only 85 lines long. And it loads the grammar, which is the rules that we looked at just a moment ago. It loads the lexicon. And then, for every line in standard input, it parses it. And what does parsing mean? Well, it does something recursive. You parse a bunch of what are called tokens. That should sound familiar. By parsing from the beginning to the end, under a special symbol called root, which we put at the top of every tree. And then the two elements of this are parsing some span of the sentence, which just tries to find the best score and the corresponding parse, where if the whole span is just one word long, then we look up the word in the lexicon. Otherwise, we try every grammar rule for the tag at the top of the parse, and we try to parse its children. So here you see parse from, calls parse children parses the first child, and then parses the rest of the children. So this is a standard recursive structure for processing trees. Except for what we're doing here is we're trying every possible rule, and we're trying every possible way in which you could push that rule over a span by dividing up its elements into the different parts. Okay, so The only trick that you need to know in order to make this run efficiently is to memorize your work. So if you've already parsed the sentence from halfway to the end, you don't want to do that twice, you just want to do it once. And now we can parse. I like dogs is a sentence starting with a personal pronoun I, followed by a verb phrase like dogs. Neat. Now this does have the capacity to disambiguate ambiguous things. So if I want to write, for instance, the big draw of a crowd, then we'll notice that the big draw is a noun phrase, and of a crowd is a prepositional phrase modifying that noun phrase. So the whole thing is a noun phrase. Versus, if I write down, I draw a picture, then I'll get a different analysis for the word draw. It will have figured out that I is the subject and draw a picture is the verb phrase. Where here, draw is a verb, whereas above, draw was a noun. So it's possible to have both of these, and it's up to our system to figure out which. Now what happens when we see a word that we've never seen before? Well, what happens in this implementation is that we call it either a noun, an adjective, or a verb, and we let the structure of the sentence figure it out. So if I write down words that didn't exist when this data set was constructed, they twerked with the twerkiest. Twerkers. It's going to figure out that twerked is a verb, twerkiest is an adjective, and twerkers is a noun. Now how did it do that? It didn't look at the endings and see that this has an S and this has an IEST and this is an ED. Instead what it did is it tried to find some tree that would fit this syntactic configuration, where it knows this is a personal pronoun, that's a preposition, and that's an article. So I'd get the same result if I said the ABCD with the ABCD, ABCD. It would figure out the only way to build a good tree using unknown words in these positions is to make the first one a verb, the second one an adjective, and the third one a noun.